the more detailed method that we're going to use to determine system stability is called our Routh-Hurwitz criterion. And so with this Routh-Hurwitz criterion, we can tell how many poles are in the left half plane, how many poles are in the right half plane, and how many poles are on the j omega axis. The one sort of caveat to this is we can't tell where the exact coordinates of the poles are. So, but not the exact location. So again, keep in mind this is telling us how many of the poles are in our general locations of left half plane, right half plane, and j omega axis, but we're not able to say we have a pole at this location. So it's relatively simple in terms of the number of steps. So our first step for checking stability is just going to be to create something called a Routh table. So after we've created the Routh table, all we have to do then is to interpret our Routh table. And so again, from interpreting our Routh table, what we're going to get is a general pole location, or general pole location. So we're going to say we have this many poles in the left half plane, this many in the right half, this many on our j omega axis. And so that's really all there is to it. So if we look at just these two simple steps for checking stability, it might seem pretty straightforward, but of course there's sort of a lot of sub-steps that go into creating our Routh table and interpreting our Routh table. So in this video, we're going to talk a little bit more about this first step, which is creating our Routh table. And then in some examples later on, we're going to come back and look at item 2, which is interpreting the Routh table results. So let's, again, first look at this creating a Routh table. As you might have guessed, what we're going to be focusing on is the denominator polynomial of our equivalent transfer function. So we want to consider our equivalent closed loop transfer function. And so we're going to look at sort of an example with a general case, and then when we come back with some more specific examples later on, we're going to plug some numbers in as opposed to variables and get a better feel for how to use that. But for right now, we're going to look at this general case where our closed loop equivalent transfer function is given by this box. We have our input on the left, R of S, our output C of S on the right. And notice I just have some general numerator polynomial N of S because we don't really care about what's going on there. What we're going to focus on is the denominator of this equivalent transfer function. Okay, so let's learn how to make our Routh table for this system. And so actually let me pull this down to the next page so we can put this system and our Routh table on the same page without having to break it up a little bit there. Okay, so the very first step is to note the order of our system. So we notice we have an s to the fourth here. So because of that, we're going to make a column, our first column, and so let me do this in blue. So our first column is going to be our s to the fourth, our s cubed, our s squared, our s to the first, and our s to the 0. So we're starting with the highest order term we had here, which was s to the fourth, and we're making a column of all the powers of s from that order down to s to the power of 0. So now we're going to populate our first two rows. So we're always going to get our first two rows from this transfer function. So for the first row, what we're going to do is we're going to look at the coefficient of our first term. So that's going to be our first term here. So we're going to have a sub 4. We're then going to skip over a term, and we're going to do a sub 2. So we have a sub 2. We then skip over a term again, and we're going to add a sub 0. Okay, so now that we've reached sort of the end of our polynomial here, we're done adding terms for that row. So what we want to do now is move on to our second row, and now we're going to look at all of the terms we skipped in the first row. So that's going to be our A3, our A1, and that's the only two, so we're going to just put in a 0 because we don't have another term beyond that. So for our second row, we're going to have A3, and A1, and then this is just going to be a 0. Okay? And so in the textbook, what you'll see is oftentimes we'll have the Routh table sort of with little a bar above and below it. you don't necessarily have to do that, but you can if you want. So these blue values are our starting values. So let me write that here explicitly. So blue is info directly from our GEQ. And so more specifically, that's directly from the denominator of our GEQ. So now what we want to do is we want to figure out the other values in this Routh table. And so let me just sort of generically call these right now. B1, B2, this is going to be 0. C1, and these two items are going to be 0. And we're going to see why that is here in a little bit. And D1 and 0 and 0. And so basically what we need to do then is just figure out what our B1, B2, C1, and D1 are. And so again, keeping in mind our blue values are coming from our GEQ, and then these black values are values that we're going to calculate. And so of course, indirectly, those are coming from the GEQ, but we're not pulling the number straight from the GEQ. So each of those entries that is not coming directly from GEQ, so all of our black values, can be found by this general equation here. So we can say x of ij, and so let me go ahead and say our I is indicating the row, and the j is indicating the column. So for instance, our A4 would be in position 1, 1. So we would say that is row 1, column 1. So we're not really counting this S term as a column. We can think of that as sort of like a header. Okay, so our general equation then is x of ij is equal to, and in the numerator, we're going to have the determinant of a 2 by 2 matrix. It's going to be the negative of that determinant. So I'm going to go ahead and write these terms, and then it's going to be more clear, I think, to just go up to the table and sort of look at some examples. So we have x with I minus 2 for our I index and 1 for our j index, x with I minus 1 for our I index and 1 for our j index. And then over here, for our second column in this matrix, we're going to have I minus 2 and j plus 1. And here we have I minus 1 and j plus 1. And then in the denominator, we're dividing the determinant of this matrix by x of I minus 1. So let me clean that up a little bit. So x of I minus 1, 1. Okay, so let's sort of figure out exactly what this equation is saying. So let's say, for instance, we're trying to calculate this B1 term here. So let's go ahead and sort of write this down here, for instance. So let's say B1 is equal to, and we know we're going to have some determinant of a 2 by 2 matrix. We know it's going to be the negative of that determinant. And so what we can see then is we're saying our B, so let me do this maybe in green over here. So if we're talking about our B, that's in our row 3, so our I would be 3, and our j would be 1. So we're in row 3, column 1, because again, we're ignoring these when we're counting our columns. So our I minus 2 then is going to be 1. This is a fixed 1. Our I minus 1 is, that's going to be 2, and this is a fixed 1. So basically, this first column, what we're saying is we're going to pull these two values that are directly above our B1, and that's going to be the first column of that determinant. So coming down here then, populating this equation, we're going to have A4 and A3. Okay, so let's come back and figure out what these other ones are. So now we have, this is going to be, again, we still have 3 and 1 for our B, for our B1 position. So our I minus 2 is going to be still 1. Our j plus 1 is now going to be 2. So for this term, we're looking at row 1, column 2. And here we're going to have row 2, column 2. And so basically what we're doing is we're going over one column. That was a mess. We're going over one column, and then we're looking at the two entries above B1. All right, so in this case, we're going to come down and populate this with our A2, A1. So A2 over A1. And then finally, this term in the denominator here is the same term that we had right here. So this is going to be a 2 and a 1. So that's just 2. Sorry, it's acting up on me. So 2 and 1. So in this case, that's just going to be this term directly above b, so our A3. So let's come down here, and we can put in our A3. Now, of course, for our 2 by 2 determinants, we're just going to take A4 times A1 minus A3 times A2. So just to show that explicitly real quick in case it's been a minute since anybody's done that. So A4 times A1 minus A2 times A3 divided by A3. And so what you can do is you can sort of incorporate this negative sign into it and just get rid of the negative sign and do A2 times A3 minus A4 times A1. Either way is perfectly fine. So this would be how we figure out the value for our B1. So now let's take a look at how we would figure out B2. So let me erase all of our green here. So of course we can use this same general equation, but now let's say we're looking at B2. So it turns out that if we're doing B2, what we're going to have is our matrix is going to be composed of our A4 and A3 and our A0 and 0. So notice that the indices here are always going to be 1. So we're always going to have 1 for our indices here. So that means we're always going back to this first column when we're populating that column of our matrix. And then our second column of the matrix here is always going to be 1 row to the right and the 2 entries above it. So we can come down here and we can populate this B2 expression, and we can say that our B2 is going to be equal to, so we'll have negative the determinant of some 2 by 2 matrix, and so from above we said that was A4 over A3 in our first column and A0 and 0 in our second column, and we divide by the A3 because that was this one sort of right above B2 in the first column. Okay, so that's how we would find B2. So using similar techniques, we could find expressions for our C1 and our D1. So just briefly, let me sort of circle what that's going to look like here. So if we're looking at our C1, now we're going to be looking at a matrix with these 4 items, and we're going to have this in the denominator. So coming down here for our C1, so you can pause the video, take a look at this closer if you need to, but we're going to have negative determinant of A3, B1, A1, B2. And then that's going to be divided by B1. Similar thing for our D1. Let me get rid of all of that real quick. So if we're looking at our D1 then, what we can say is we're going to have our B1 and C1 and our B2 and 0. Okay, so our D1 is going to be equal to negative the determinant of our 2 by 2 matrix, B1 and C1, B2 and 0, and so that's divided by C1. So of course what you can see is that our C and our D calculation depends on having a corrected calculation for our previous value. So it's very important you're careful as you're doing this. So another thing that we can get from this general form of the equation is we can figure out why it is that I sort of arbitrarily, maybe it looks like, put in these zeros over here. So why did I just randomly put zeros there? Well, of course, it wasn't random. So let's say maybe instead of a 0 there, I put a C2. So if I have C2, I can come back and use this general equation. If it'll let me write C2. There we go. So I can use this general equation to find my C2 value. And so for that, if I'm looking at C2, what I'm going to be doing is I'm going to be going back to my first row, or sorry, the first column, the 2 rows above, and then I'm going to be going to the right 1 row, to the right 1 column, 2 rows above, and so I get something that looks like this. So what that is going to give me is I'm going to have C2 is equal to negative determinant of A3 B1 0 0 over B1, and of course what we're going to see, we'll have A3 times 0 minus B1 times 0, so this is just going to be equal to 0. And so that's true of everywhere else where I've added zeros in there. And so, of course, we could sort of add zeros for all of these terms as far as we want, but we don't need to explicitly show that. So one other note too is that this general equation isn't in your textbook, so you don't need to know this. It's sort of explained a little bit differently in your text, but I think that this general equation is a little more helpful. But of course, once we go through examples and get some more practice, it'll become sort of second nature to create these Routh tables.